Imagine a world floating in the cosmic void, just 4.2 light years from where you're sitting right now. This planet, slightly bigger than our own Earth, dances around a crimson star in an eternal waltz. Scientists suspect that flowing water might be painting landscapes across its surface at this very moment. This mysterious realm goes by the name Proxima Centauri b, and it marks only the opening chapter in humanity's most monumental revelation. We're talking about distant worlds spinning beyond our solar system's borders, places where life itself might be taking its first breath. Tonight, we're embarking on an expedition to realms where hidden seas slumber beneath frozen armor. We'll visit places where one hemisphere bakes under endless sunshine, while its twin shivers in everlasting shadow. We'll explore atmospheres that could be dancing with the very molecules of existence, from spheres where precious gems fall like raindrops to domains where sunrise comes just once, in what we'd call centuries. Every stop edges us closer to cracking the ultimate riddle. But before we blast off into this cosmic frontier, smash that like button and hit subscribe, because this adventure will carry us beyond any boundary humans have ever crossed. The age-old question haunts us still: meet end, do we stand alone in this infinite universe? The key to that mystery might be spinning silently on one of these remarkable distant shores. Still yourselves for what's coming. Our launch sequence begins now. Envision the cosmic cookbook for creating life itself. The recipe calls for exactly 3 essential elements, where mastering their perfect balance determines whether a world transforms into Eden or becomes a living nightmare. The opening ingredient appears deceptively straightforward: liquid water. Yet this is where complexity creeps in. Water maintains its liquid form only within what researchers have dubbed the Goldilocks zone. This represents that precise orbital sweet spot where temperatures dance between freezing and boiling points. Venture too close to your host star, and planetary oceans evaporate into the void like mist escaping a boiling pot. Drift too far into the cold depths of space, and everything crystallizes into solid ice, transforming your world into a cosmic snowball. Our Earth occupies this magical position roughly 93 million miles from our life-giving sun, where water performs its incredible 3-act performance: P2 performance, flowing as liquid, floating as vapor, and freezing as ice, sometimes all within the same moment. The second crucial component demands more than just any ordinary atmosphere. Success requires precisely the right cocktail of gases that can capture warmth like nature's perfect thermal blanket, while still permitting life-giving light to penetrate the surface. Picture wrapping yourself in the ideal winter jacket, that's substantial enough to maintain your body heat, yet breathable enough to prevent dangerous overheating. Venus possesses an atmosphere, but it's so overwhelmingly packed with carbon dioxide that surface temperatures soar to 900 degrees Fahrenheit, scorching enough to liquefy metal. The third ingredient might catch you off guard completely: a planetary magnetic field. Without this invisible protective barrier, lethal cosmic radiation systematically strips away atmospheric molecules one by one, like a thief stealing air itself. Mars once boasted rushing rivers and possibly vast oceans painting its surface blue, but when its magnetic shield faltered and died, relentless solar winds gradually pilfered its atmospheric treasure, abandoning the frozen wasteland we observe today. Here's what makes this cosmic recipe so extraordinarily rare. These 3 components must harmonize flawlessly for millions, sometimes billions of years without interruption. A planet requires an orbital path that neither swings dangerously close nor drifts perilously far from its stellar companion. It needs sufficient mass to clutch its atmospheric envelope tightly, yet not so massive that it balloons into a gas giant like mighty Jupiter. The host star itself must remain calm enough to avoid bombarding the planet with lethal energy bursts, while staying active enough to deliver consistent, steady power. Researchers have unveiled over 5,000 planets spinning around distant stars, yet fewer than 50 nestle within that precious zone where all 3 ingredients might coexist in harmony. Each represents a potential Earth twin, a realm where alien heavens might shelter alien oceans, where life's chemistry could be penning its own epic tale right at this moment. The challenge transforms into locating these needle-in-a-haystack worlds scattered across space's vast emptiness, then determining which ones actually brew the right conditions beneath their mysterious cloud covers. We've constructed space telescopes capable of sensing the most subtle dimming of starlight when a planet glides across its sun's face, measuring worlds so impossibly distant that their ancient light requires years of travel to reach our instruments. But among all these remote possibilities, one particular planet emerges as our closest companion in the quest for life. Slightly over 4 light-years away, a world circles the nearest star to our home solar system, and the evidence suggests something truly extraordinary might be unfolding there. During 2016, astronomers detected something that revolutionized everything. A planet merely twice Earth's size completing its orbit around the closest star to our solar system every 11 days. Proxima Centauri b hangs 4.2 light-years from home, which means even traveling at light's maximum speed would still demand over 4 years to reach this world that could shelter the nearest alien life to Earth. Here's what makes this breakthrough so absolutely mind-blowing. This planet orbits directly within its star's habitable zone, where temperatures could permit liquid water to flourish on the surface. But Proxima Centauri differs dramatically from our Sun. It's a red dwarf star, smaller and cooler, radiating dim crimson light that would make midday on this world resemble Earth's twilight hours. The planet confronts a challenge that would terrorize any space explorer. Proxima Centauri b remains tidally locked to its star, meaning one hemisphere endures eternal daylight, while its opposite side suffers in permanent darkness. Picture standing at the boundary between these two extremes, where the sun hangs motionless in alien skies like a dim scarlet eye, never climbing or descending, while behind you stretches an endless frozen wilderness beneath foreign constellations. Temperatures on the sunlit side could climb to 140 degrees Fahrenheit, while the shadow side plummets to -40 degrees. But here's where fascination takes hold. If this world possesses an atmosphere dense enough to circulate heat effectively, the boundary region between eternal day and endless night might sustain temperatures ideal for liquid water. Scientists have named this the Terminator line, and it could represent life's final battleground. The genuine mystery lies hidden beneath the surface. Computer simulations suggest that if Proxima Centauri b maintains even a thin atmospheric layer, wind currents could generate a surprisingly steady climate. Heated air would ascend on the day side, stream toward the night side, cool dramatically, and return in a colossal circulation system that could maintain the entire planet at habitable temperatures. Recent observations hint at something even more thrilling. This world might possess a magnetic field powerful enough to shield it from its star's violent eruptions. Yet Proxima Centauri harbors a violent secret. This crimson star unleashes solar storms 10 times more ferocious than our sun's most devastating outbursts, bombarding its planetary companion with lethal cosmic radiation. Without adequate shielding, these stellar tantrums would obliterate any atmospheric protection within mere millions of years. However, if Proxima Centauri b has managed to preserve its gaseous envelope throughout the 4.8 billion years since this stellar system's birth, that implies something truly extraordinary is unfolding there. This distant world might cradle vast oceans, dynamic weather systems, perhaps even seasonal cycles, as its slightly oval-shaped orbit carries it nearer to and farther from its stellar parent. The gulf separating us from this realm creates both tantalizing possibilities and maddening limitations. While 4.2 light-years seems practically next door in astronomical measurements, it actually represents 25 trillion miles of absolute nothingness stretching between worlds. Our swiftest spacecraft would demand more than 70,000 years to bridge this cosmic chasm to reach Proxima Centauri b. Yet this same proximity offers hope that advanced future telescopes might actually capture direct images of its surface and dissect its atmospheric composition for biological signatures. But this solitary world represents merely our first stop on an epic voyage through the universe's hidden treasures. Venturing deeper into space's mysteries, an entire family of 7 planets awaits our discovery. Each one roughly matching Earth's dimensions, these worlds remain trapped in an intricate gravitational ballet around a star so diminutive and cool that all 7 spheres cluster closer to their sun than Mercury approaches ours. Stretching across 39 light-years of space from our home, 7 worlds dance so intimately close to each other that standing on any planet's surface would reveal its siblings appearing larger in alien skies than our moon appears to Earth-bound observers. The TRAPPIST-1 system compresses these 7 Earth-sized planets into a region smaller than the gap between our Sun and Mercury, orchestrating a cosmic performance where each world's gravitational pull influences its neighbors in flawless mathematical precision. This stellar arrangement operates unlike anything witnessed in our home solar system. TRAPPIST-1 itself belongs to what astronomers classify as an ultra-cool dwarf star, so compact and faint that 12 copies could nestle comfortably inside our Sun's volume. It consumes hydrogen fuel so gradually that it will continue radiating light for trillions of years, persisting long after our Sun expands into a red giant and perishes. The star's weak crimson radiance means all 7 planets orbit within what would constitute the habitable zone surrounding a typical star. Here's where this system becomes genuinely bizarre. These planets remain locked in what researchers term orbital resonance, meaning their pathways synchronize like cosmic clockwork. But every 8 complete circuits the innermost planet makes, the adjacent planet completes exactly 5 orbits, and this mathematical pattern continues outward throughout the entire system. It's as though some universal architect deliberately engineered this arrangement to maintain stability across billions of years. The 3 planets occupying the middle positions in this chain bed-designated TRAPPIST-1d, TRAPPIST-1e, and TRAPPIST-1e, and TRAPPIST-1f nestle perfectly within the zone where flowing water could paint their surfaces. Yet each world confronts the identical challenge facing Proxima Centauri b. They remain tidally locked with one hemisphere perpetually facing their star, while the opposite hemisphere suffers in endless darkness. Researchers have employed both the Hubble Space Telescope and the revolutionary James Webb Space Telescope to examine these planets' atmospheric layers as they transit across their star's face. The collected data unveils something captivating. At least 3 of these worlds might possess substantial gaseous envelopes, and one displays potential evidence of water vapor suspended in its atmospheric mix. The genuine puzzle revolves around TRAPPIST-1e, the 4th planet counting outward from the star. This world absorbs almost precisely the identical amount of stellar energy that Earth receives from our Sun, establishing it as potentially the most Earth-like planet humanity has ever identified. Computer simulations indicate it could maintain a dense atmosphere capable of redistributing thermal energy around the planet, generating temperate conditions even across the permanently shadowed hemisphere. If you could somehow journey to TRAPPIST-1e, the experience would transcend anything possible on Earth. The star would dominate the sky, appearing roughly 3 times our Sun's apparent size, radiating deep crimson light that would bathe the landscape in what resembles eternal firelight. The remaining 6 planets would suspend themselves in the heavens like brilliant gemstones, some displaying crescent phases, others showing complete illuminated disks, their positions constantly shifting as they pursue their cosmic choreography. The gravitational interactions weaving through these 7 worlds generate another phenomenon that thrills scientists: tidal heating. As each planet's orbital path gets stretched and compressed by its neighbor's gravitational embrace, the resulting internal friction could warm planetary cores sufficiently to maintain liquid underground seas, even on worlds appearing too frigid at their surfaces. Recent atmospheric investigations have disclosed that these planets harbor varying quantities of water, suggesting each world narrates its unique tale of formation and development. Some might qualify as water worlds concealing profound oceans, while others could manifest as rocky desert planets or ice-encrusted moons sheltering hidden seas. But among all the worlds humanity has uncovered, one planet emerges as Earth's most precise twin, circling a star so remarkably similar to our Sun that scientists christened it Earth's older cousin. Positioned 1,400 light-years away, this planet requires 385 days to complete one orbital journey around a star, nearly identical to our Sun, establishing seasons and yearly cycles so closely matching Earth's that you could practically use an identical calendar. Kepler 452b travels within its star's habitable zone at precisely the correct distance for liquid water to flourish, and this world has maintained this perfect position for 6 billion years, 9.5 billion years longer than Earth has even existed. Here's what renders this planet absolutely extraordinary. Its host star, Kepler 452, burns at almost identical temperature and luminosity to our Sun, delivering consistent, reliable energy that could nurture complex life across billions of years. The planet itself measures approximately 1.6 times Earth's diameter, qualifying it as what scientists classify as a super-Earth substantial enough to possess a denser atmosphere capable of trapping heat and shielding the surface from harmful radiation. The gravitational force on Kepler 452b would feel roughly twice as intense as Earth's pull. This means if you weigh 150 pounds here, you'd tip the scales at around 300 pounds there. Your muscles would eventually adapt over time, but activities like jumping or climbing would demand significantly greater effort. The enhanced gravity also enables this world to retain a thicker atmospheric blanket for extended periods, potentially creating more consistent weather patterns than Earth experiences. This planet's year extends just 20 days beyond an Earth year, and its orbital position sits in nearly identical relationship to its star, as Earth maintains relative to our Sun. Should Kepler 452b experience seasonal cycles, they would mirror Earth's familiar rhythm. Spring, summer, autumn, and winter would unfold across roughly identical timeframes as our planetary seasons. Trees, assuming they flourish on this distant world, might display growth patterns remarkably similar to Earth's woodland giants, complete with annual rings marking each year's passage. The age of this stellar system raises mind-bending questions about what evolutionary marvels might have emerged there. Earth's most sophisticated life forms have existed for merely a few 100 million years, yet Kepler 452b has enjoyed 6 billion years to nurture biological development. If living organisms gained their foothold on this world during its early epochs, we might be gazing upon a planet where evolution has wielded 50% additional time to craft astounding diversity and complexity beyond our wildest imagination. Computer simulations propose that if Kepler 452b began with equivalent water reserves as Earth, it could have matured into an ocean-dominated world featuring small land masses, scattered like emerald jewels across its azure surface. The enhanced gravitational pull would generate more spectacular tidal phenomena, potentially creating vast tidal pools where primitive life could have established its foundation before migrating to the open seas. The host star, Kepler 452, burns approximately 1.5 billion years older than our Sun, while radiating slightly more brilliantly. This translates to the planet receiving roughly 10% more stellar energy than Earth currently absorbs. This surplus energy could fuel more vigorous weather systems, more powerful storm formations, increased evaporation rates, and more spectacular cloud architectures that might appear from space as swirling white spirals dancing against deep blue oceanic backdrops. Recent investigations of this system reveal something even more fascinating. As Kepler 452 continues aging, it gradually intensifies in brightness and temperature, mirroring the future path our Sun will follow. Kepler 452b might be offering us a preview of Earth's destiny roughly 1 billion years hence, when our Sun's escalating luminosity begins vaporizing our oceans and rendering our planet uninhabitable. If this world has nurtured life throughout its 6 billion year journey, that life now confronts the identical challenge Earth will face in the distant future, adapting to a progressively warming planet as its stellar companion grows increasingly luminous. The survival strategies life develops on Kepler 452b might provide blueprints for how future Earth organisms could endure similar transformations. But while Kepler 452b offers glimpses into Earth's potential future, another recently unveiled world delivers hope for discovering life much nearer to our cosmic neighborhood. Positioned just 137 light-years away, a planet measuring 1.5 times Earth's dimensions completes its stellar orbit every 19 days, nestled precisely within the zone where flowing water could paint its surface. Tuai 715b represents among the most recent additions to our catalogue of potentially life-supporting worlds. Unveiled in late 2023 through NASA's Transiting Exoplanet Survey satellite, this realm circles a red dwarf star designated Tuai 715. Much smaller and cooler than our Sun, This stellar companion requires the planet to huddle closely to receive adequate warmth for liquid water. The 19-day orbital period positions 2I 715b at roughly equivalent distance from its star, as Mercury maintains from our Sun. However, because its host star burns so much cooler, the planet absorbs precisely the right amount of energy to sustain moderate temperatures. Here's what renders this discovery exceptionally thrilling. Tadai 715b resides directly within what astronomers designate the conservative habitable zone, the region where scientists maintain highest confidence that liquid water could flourish. Many potentially habitable planets dance along the edges of this zone, where minor atmospheric variations could push them toward freezing or boiling. Tadai 715b faces no such uncertainty. The planet's dimensions suggest it could qualify as a super-Earth hosting a substantial atmospheric envelope, possibly dense enough to redistribute heat around the planet and generate a greenhouse effect, maintaining stable temperatures. Computer models indicate that if this world possesses an atmosphere resembling Earth's but 2 to 3 times thicker, it could preserve liquid water even across its night hemisphere. Because 2I 715b orbits so relatively close to Earth in cosmic measurements, it represents an ideal candidate for atmospheric analysis using our most sophisticated telescopes. The James Webb Space Telescope can identify the chemical signatures of gases within this planet's atmosphere as it transits across its star's face, potentially revealing whether water vapor, oxygen, or other biological activity indicators exist within its atmospheric mixture. The star 2I 715 presents both benefits and obstacles for life. Red dwarf stars burn for trillions of years, delivering stable energy for vastly longer periods than stars resembling our Sun. However, they typically generate violent stellar outbursts during their youth that could obliterate planetary atmospheres. At 5 billion years old, 2I 715 has matured into a calmer phase, increasing the likelihood that its planet has preserved whatever atmospheric protection it originally possessed. Recent observations suggest that 2I 715b might not orbit alone. Scientists have detected hints of a second planet inhabiting this system, potentially even more Earth-like than the first discovery. If confirmed, this would establish 2I 715 as among the closest systems hosting multiple potentially habitable worlds, providing an unprecedented laboratory for studying how planets within identical systems can develop distinctly different characteristics. The planet's rapid 19-day orbit creates an intriguing consequence. Should Tycho 715b experience seasons, they would transform incredibly rapidly by Earth standards. Seasonal fluctuations might persist for mere days, generating swiftly shifting weather patterns that could challenge any life forms attempting to adapt to changing conditions. Temperature variations across the planet's surface could establish diverse climate zones within relatively compact areas. Equatorial regions might remain warm enough for liquid water throughout the year, while polar territories could stay frozen, creating ice caps that advance and retreat with the planet's swift seasonal transitions. For astronomers, 2I 715b represents something invaluable: MITRE, a nearby laboratory where we can examine our theories about habitability and atmospheric evolution. Its proximity means we might detect radio signals if intelligent life exists there, and future space telescopes could potentially photograph its surface with sufficient detail to identify continents, oceans, and weather patterns. But while 2I 715b offers hope for finding life relatively close to home, another world farther out in space has already provided us with something extraordinary: the first confirmed detection of water vapor in a potentially habitable planet's atmosphere. Stretching 124 light-years from Earth, a planet 8 times more massive than our world travels through its star's habitable zone, and in 2019, the Hubble Space Telescope detected something that sent shockwaves rippling through the scientific community. Water vapor dancing within its atmospheric embrace, K218b, transformed into the first potentially habitable exoplanet, where we confirmed the existence of water suspended in alien air, elevating it from merely another distant sphere into a realm where life's chemistry might actually be flourishing. This breakthrough represented a pivotal moment in our quest for life beyond Earth's boundaries. For decades, researchers could only theorize about what mysterious elements might swirl within the atmospheric layers of remote planets. But K218b delivered the first concrete evidence that worlds nestled in habitable zones can indeed shelter water vapor. This planet presents a puzzle that challenges our fundamental understanding of what makes a world livable. K218b qualifies as a mini Neptune, a category of planet larger than Earth yet smaller than Neptune, wrapped in a substantial atmospheric envelope that might consist primarily of hydrogen and helium. Traditional scientific models suggested such worlds couldn't sustain liquid water on their surfaces because their dense atmospheres would trigger runaway greenhouse effects, creating temperatures too scorching for life to survive. However, recent computer modeling reveals a surprising twist. If K218b possesses the ideal atmospheric cocktail containing sufficient water vapor and other greenhouse gases, it might maintain moderate temperatures despite its imposing size. The planet could even host liquid water clouds floating within its atmosphere, creating aerial oceans suspended in the sky like ethereal seas dancing among the stars. The water vapor breakthrough emerged from a technique called transmission spectroscopy, where researchers analyze starlight filtering through planetary atmospheres as worlds pass in front of their stars. Different gaseous compounds absorb specific wavelengths of light, generating unique fingerprints that reveal atmospheric composition. The water vapor signature from K218b proved unmistakable: minus hydrogen and oxygen bonded together in the precise proportions that create water. K218b completes its stellar orbit every 33 days, positioning it directly within the habitable zone where liquid water could flourish. The host star K218 burns as a red dwarf roughly half our sun's size, providing steady energy for potentially billions of years. The planet receives approximately the same amount of stellar energy that Earth absorbs from our sun, suggesting moderate surface temperatures could exist there. Here's where this cosmic tale becomes even more captivating. In 2023, the James Webb Space Telescope conducted another examination of K218b and detected possible evidence of additional atmospheric gases, including carbon dioxide and possibly even hydrogen sulfide or other sulfur compounds. These gases could indicate active geological processes happening beneath the surface, or more thrilling still, Milo's biological activity. The planet's substantial mass generates gravity, roughly 2.3 times stronger than Earth's, which would dramatically influence how atmospheric layers and weather systems behave. Enhanced gravity would create denser air at the surface and might enable more massive cloud formations and more intense weather patterns than anything witnessed on Earth. If K218b conceals a solid surface beneath its thick atmospheric blanket, that surface might be completely submerged beneath water, creating a world-spanning ocean. The intense pressure from the dense atmosphere could allow water to remain liquid at higher temperatures than on Earth, potentially creating a hot, humid environment that could still nurture certain forms of life. The detection of water vapor on K218b unlocked new possibilities for discovering life throughout our galaxy. It proved that our telescopes can identify biosignature gases in the atmospheres of distant worlds, bringing us one step closer to answering whether we exist alone in the universe. Researchers now employ K218b as a prototype for studying atmospheric chemistry on potentially habitable worlds. Each new observation teaches us more about how atmospheres function on planets drastically different from Earth, expanding our definition of what qualifies a world as suitable for life. But while K218b revealed water floating in alien skies, our next destination carries us to an even more bizarre world. A planet trapped in eternal twilight, where one hemisphere burns under a crimson sun that never sets, while the opposite hemisphere freezes under stars that never fade. Position 23 light-years away, a planet slightly larger than Earth experiences a phenomenon that would revolutionize human civilization. One hemisphere bathes in perpetual daylight under a red dwarf sun, while the other hemisphere shivers in permanent darkness under alien constellations. Gliese 667 cc remains tidally locked to its star, creating a world where the sun never climbs or descends, hanging motionless in the sky like a crimson eye that never blinks. This planet circles its star every 28 days at a distance, closer than Mercury approaches our sun, but its stellar companion burns so cool and dim that Gliese 667cc absorbs precisely the right amount of energy for liquid water to exist across its surface. The result creates a world divided into 3 distinct climate zones that could each shelter completely different forms of life. The day side of Gliese 667cc experiences constant illumination under a sun that appears roughly twice as large as our sun looks from Earth, radiating deep red light that would make familiar landscapes appear alien and mysterious. Temperatures on this hemisphere could soar to 130 degrees Fahrenheit, generating vast deserts where any surface water would evaporate rapidly. But underground water reserves might provide oases where life could flourish. The night side tells a completely different story. Here, temperatures plummet to -80 degrees Fahrenheit or lower, cold enough to freeze carbon dioxide from the atmosphere and create dry ice snow. But this frozen hemisphere would offer spectacular views of the cosmos with no sun to wash out the sky. The stars would shine with crystal clarity, and any moons orbiting Gliese 667cc would cast shadows and create tides across this eternally dark hemisphere. Between these two extremes lies the most fascinating region of all, the Terminator Zone, the narrow band where day meets night in perpetual twilight. Here the red sun hangs just at the horizon, painting the landscape in shades of orange and crimson, while temperatures hover near water's freezing point. This twilight zone could be where liquid water persists, where weather patterns create clouds and storms, and where life might find its most comfortable home. Computer models suggest that if Gliese 667cc possesses an atmosphere thick enough to circulate heat around the planet, powerful wind systems would develop between the scorching day side and frigid night side. Heated air would ascend from the illuminated hemisphere, stream toward the shadowed side at elevated altitudes, cool and descend, then cycle back to the sunlit side at surface level, establishing enormous circulation systems that could regulate temperatures across the entire planetary surface. The planet's gravitational pull measures roughly 4.5 times stronger than Earth's, which would generate several fascinating phenomena. The denser atmosphere this enhanced gravity permits could capture more thermal energy and produce more spectacular weather patterns. Precipitation would plummet faster and strike with greater force. Wind currents would feel more intense, and the elevated atmospheric pressure might enable water to stay liquid at higher temperatures than we experience. The red dwarf star Gliese 667c offers both advantages and obstacles for life. Red dwarf stars burn for trillions of years, delivering consistent energy vastly longer than stars resembling our Sun. However, they typically unleash violent stellar outbursts, particularly during their youth. Gliese 667c has matured into a relatively peaceful phase, yet occasional flares could still assault the planet with harmful radiation. If intelligent life developed on Gliese 667cc, the civilization would emerge in ways completely foreign to human experience. They might construct cities within the Terminator Zone, where temperatures remain moderate, harnessing the temperature contrast between day and night sides to produce energy. Their calendar would rely on orbital cycles rather than sunlight patterns, and they would never witness sunrise or sunset. The perpetual twilight zone could establish unique evolutionary pressures that generate life forms unlike anything on Earth. Plants might adapt to efficiently absorb the dim crimson light, developing black or deep purple foliage instead of green leaves. Animals might develop superior night vision to navigate the constant twilight, or they might depend more heavily on alternative senses like hearing or touch. But compared to the bizarre seasonal rhythms on our next destination, even permanent twilight might seem ordinary. Farther out in space, a super-Earth experiences seasons that persist longer than most creatures live on Earth. Positioned 42 light-years from Earth, a world 7 times more massive than our planet requires 200 days to complete one stellar orbit. But here's where it becomes extraordinary. The planet's tilted axis generates seasons lasting 25 Earth years each, long enough for human generations to be born, live complete lives, and perish during a single spring. HD 40,307G challenges our comprehension of how seasonal variations influence life and climate on a planetary scale. This super-Earth orbits at the distant edge of its star's habitable zone, receiving barely sufficient energy to potentially sustain liquid water across its surface. The host star, HD 40307, burns slightly cooler and dimmer than our Sun, which means the planet must maintain its orbit in the precise sweet spot where temperatures hover right around water's freezing threshold. Minor changes in the planet's distance from its star during its slightly oval-shaped orbit could determine the difference between a world shrouded in ice and one featuring flowing rivers. The planet's tremendous size creates gravity, approximately 2.4 times stronger than Earth's, which carries profound consequences for its atmosphere and weather systems. The enhanced gravity enables HD 40307G to retain a much thicker atmospheric envelope than Earth possesses, potentially creating a greenhouse effect that maintains the planet warm enough for liquid water even at its distant orbital position. Here's where the decades-long seasons establish a unique scenario. As the planet's tilted axis directs different hemispheres toward the star during its 200-day orbit, one hemisphere experiences 25 years of summer, while the other endures 25 years of winter. The temperature contrast between these hemispheres would generate weather patterns completely unlike anything witnessed on Earth, massive storm systems that could persist for years, migrating between hemispheres as the seasons gradually shift. The extended seasonal cycles would create opportunities for life that don't exist on Earth. Plants could evolve to exploit the decades-long growing seasons, potentially achieving enormous proportions during the 25-year summers. Forests might develop that flourish for decades, then enter dormancy for decades, creating landscapes that transform completely over a century's course. Animal life would confront unique challenges on HD 40307G. The species might evolve migration patterns spanning entire generations, with offspring following routes their parents never completed. Some creatures might develop extended lifespans to survive the prolonged winters, while others might create extreme hibernation strategies lasting for decades. The thick atmosphere generated by the planet's powerful gravity could produce weather phenomena that dwarf anything on Earth. Hurricane-like storms might endure for years at a time, and the atmospheric pressure at sea level could be several times higher than Earth's, allowing liquid water to exist at temperatures well above 212 degrees Fahrenheit. Computer simulations suggest that HD 40307G might possess a highly active geological system due to its large size and mass. The planet's interior would generate more heat than Earth's core, potentially leading to increased volcanic activity and more dramatic mountain-building processes. The landscape might change significantly, even within the lifetime of long-lived organisms. The planet's position at the outer edge of the habitable zone means it might experience periods where its entire surface freezes during the global winter season, only to thaw completely during global summer. This creates the possibility of a world where ice ages and warm periods alternate every 50 years in a predictable cycle. If HD 40307G hosts moons, they would experience even more extreme seasonal variations as they orbit a planet that itself endures decades-long seasons. The gravitational interactions between the planet and its moons could create tidal heating that maintains liquid water available even during the longest winters. The implications for any civilization that might evolve on HD 40307G are staggering. Their technology and culture would need to accommodate climate changes spanning multiple generations. They might develop advanced long-term planning capabilities that far exceed anything humans have achieved, building infrastructure designed to endure through decades of winter, or planning agricultural strategies that account for 25-year growing seasons. But while HD 40307G demonstrates how extreme seasonal variations might affect life, our next destination carries us to an even more challenging world. A planet so distant from its star that it should be frozen solid, yet might harbor liquid water in hidden underground oceans. Stretching 1,194 light-years away, a planet just over one-third larger than Earth orbits at the very outer edge of its star's habitable zone, where surface temperatures likely hover around -50 degrees Fahrenheit year-round. Kepler 442b should be a frozen wasteland. Yet researchers believe this remote world might shelter enormous underground oceans maintained in liquid form by the planet's own internal thermal energy, establishing a concealed biosphere that could nurture life in eternal darkness. This world completes its stellar circuit every 112 days, positioning it at roughly equivalent distance from its Sun as Venus maintains from ours. However, Kepler 442b's host star burns significantly cooler and dimmer than our Sun, delivering only approximately 70% of the energy that Earth absorbs. The outcome produces a planet where any surface water would crystallize completely, generating ice sheets that could stretch from polar region to polar region. The planet's dimensions hold the secret to its potential livability. Kepler 442b contains roughly twice Earth's mass, establishing stronger gravitational pull that helps the planet clutch a dense atmosphere. This atmospheric envelope could capture sufficient thermal energy to prevent the planet from becoming entirely frozen. More crucially, the additional mass ensures the planet's interior remains heated for billions of years longer than smaller worlds. Here's where the concealed ocean hypothesis becomes fascinating. The breakdown of radioactive materials in Kepler 442b's core, combined with tidal heating from its slightly oval-shaped orbit, could produce adequate internal warmth to liquefy ice at depths of merely a few miles beneath the surface. Computer simulations indicate that underneath the frozen shell, this world might shelter liquid water seas deeper than any ocean on Earth. These subsurface seas would exist in absolute darkness, heated from below by geothermal vents that could supply energy for life. On Earth, we've uncovered flourishing ecosystems surrounding deep ocean volcanic vents where sunlight never reaches. Organisms in these environments extract energy from chemical reactions rather than photosynthesis, establishing food webs based on bacteria that transform sulfur compounds and other chemicals into usable energy. Kepler 442b might shelter similar ecosystems on a planetary magnitude. The boundary between the liquid ocean and the rocky seafloor could accommodate countless hydrothermal vents, establishing chemical oases where exotic life forms develop in ways completely independent of surface conditions. These organisms might never realize that a star exists, spending their entire existence in the warm, dark waters beneath miles of ice. The planet's thick atmospheric layer could generate another surprising possibility. Even though surface temperatures remain well below freezing, atmospheric pressure might be elevated enough to permit liquid water to exist in deep valleys or crater basins, establishing isolated pockets where surface life could survive. These regions would resemble oases in a frozen wasteland, connected to the vast underground seas. The extended orbital period means that Kepler 442b experiences seasons lasting approximately 28 Earth days each. While these seasonal shifts wouldn't be dramatic enough to melt the surface ice, they could establish thermal cycles that circulate liquid water up and down through the planet's crust, mixing nutrients between the surface and the deep oceans. If life exists in Kepler 442b's hidden oceans, it might be incredibly diverse and sophisticated. With billions of years to develop in a stable, protected environment, these organisms could establish complex ecosystems that surpass anything we observe on Earth. The constant darkness would favor life forms that communicate through sound waves, chemical signals, or even electrical discharges rather than visual displays. The planet's powerful gravity would establish unique conditions for any life that did evolve there. Organisms would need to be more resilient to survive the increased pressure, and any creatures that evolved gas-filled swim bladders would require much stronger structures to maintain buoyancy in the high-gravity environment. Recent advances in telescope technology might soon enable us to detect signs of these hidden biospheres. If Kepler 442b's underground oceans occasionally release water vapor or other gases through fractures in the ice, space telescopes could identify these atmospheric signatures and confirm the presence of subsurface water. But while Kepler 442b might conceal its oceans beneath ice, our next destination confronts a completely different challenge: surviving the violent radiation storms from a star that regularly assaults its planet with lethal energy. Positioned just 13.8 light-years from Earth, a rocky planet 4 times more massive than our world orbits perilously close to a red dwarf star that unleashes violent radiation storms, powerful enough to strip away atmospheres and sterilize surfaces. Wolf 1061c sits precisely on the inner edge of its star's habitable zone, where liquid water could theoretically exist, but the planet wages a constant battle against stellar winds and flares that would make survival an extraordinary challenge for any life forms bold enough to call this world home. This super-Earth completes one orbital journey around its star every 17.9 days, racing through space at velocities that would make Mercury appear sluggish. The close orbit positions Wolf 1061c at roughly 1/20th, the distance between Earth and our Sun, so close that the star would appear 25 times larger in the sky than our Sun appears from Earth, dominating the horizon like a massive crimson wall of fire. Wolf 1061, the star at this system's center, exemplifies the dangerous side of red dwarf stars. While these compact stars burn for trillions of years and seem perfect for supporting long-term biological evolution, they tend to be magnetically volatile, producing stellar flares that can amplify their brightness by 10 times or more within minutes. When these flares strike Wolf 1061c, they bombard the planet with X-rays and ultraviolet radiation intense enough to shatter water molecules in the atmosphere. The planet's substantial mass works both for and against its prospects for habitability. The stronger gravity helps Wolf 1061c retain whatever atmosphere it possesses, but it also means that any atmosphere would be denser and potentially more susceptible to chemical breakdown by radiation. Recent computer models suggest that if this world began with an Earth-like atmosphere, it might have lost most of its water vapor and oxygen to space over the past few billion years. Here's where the narrative becomes intriguing. Wolf 1061c might represent a planet in transition, a world that once possessed oceans and a thick atmosphere, but is gradually losing both to the relentless assault of stellar radiation. If this process is occurring slowly, the planet might still harbor liquid water in protected regions like deep valleys or underground caverns, where the atmosphere remains dense enough to maintain stable conditions. The planet's rapid orbit creates another unique scenario. The 17.9-day year means that seasonal changes, if they exist, would flash by in a matter of Earth days. Any organisms that developed on Wolf 1061c would need to adjust to astonishingly rapid environmental cycles, or they would need to discover stable refuges that don't fluctuate with the planet's swift orbit. Researchers have employed computer simulations to investigate what might occur to water on Wolf 1061c during the most ferocious stellar outbursts. The models indicate that while the planet's sun-facing hemisphere confronts the complete intensity of the radiation tempests, water on the shadow side might endure in a perpetual freeze-thaw rhythm. As the planet spins, ice on the night side liquefies when it rotates into sunlight, generating temporary streams and pools that solidify again when they rotate back into shadow. The magnetic field intensity of Wolf 1061c could decide whether this world possesses any opportunity for nurturing life. Earth's magnetic shield deflects most harmful radiation from our Sun, but Wolf 1061c confronts a far more turbulent stellar environment. If the planet maintains a robust magnetic field produced by its iron core, it might create a protective barrier that shields at least portions of its surface from the most devastating radiation storms. Recent observations indicate that Wolf 1061c might not be entirely atmosphere-free. Spectroscopic examination hints that the planet might still preserve a thin atmospheric layer, possibly containing heavier gases that resist being swept away by stellar winds. Carbon dioxide, water vapor, and nitrogen could survive in this thin atmosphere, establishing surface pressures barely elevated enough to permit liquid water to exist in deep depressions. The planet's closeness to Earth establishes it as a perfect candidate for detailed investigation. Future space telescopes will analyze Wolf 1061c's atmosphere in real time, observing how it reacts to stellar flares and measuring whether water vapor appears and vanishes as the planet rotates. These observations could teach us how planetary atmospheres develop around active stars. If life does exist on Wolf 1061c, it would need to be extraordinarily hardy. Organisms might evolve to dwell underground, surfacing only during peaceful intervals between stellar storms. They might develop advanced DNA repair systems to correct radiation damage, or they might evolve to harness the high-energy radiation as an energy source rather than viewing it as a danger. But while Wolf 1061c demonstrates how life might endure in a hostile radiation environment, Our expedition now carries us to a more tranquil world where the challenges are more nuanced and the possibilities for life even more captivating. Positioned 41 light-years from Earth, a planet nearly 7 times more massive than our world circles a peaceful red dwarf star every 25 days. And recent observations suggest something extraordinary. This dense, rocky super-Earth might have succeeded in retaining a substantial atmosphere despite billions of years of stellar radiation. LHS 1140b represents a triumph story in planetary survival, live at world that appears to have prevailed in the struggle against atmospheric erosion that devastates so many other planets. This planet's remarkable density distinguishes it from other super-Earths we've uncovered. LHS 1140b compresses almost 7 Earth masses into a world only 1.7 times Earth's diameter, establishing a density that suggests a composition primarily of iron and rock with minimal water content. The result produces a planet with surface gravity roughly 5 times stronger than Earth's, where atmospheric pressure at sea level could be 20 times higher than what we experience. The thick, high-pressure atmosphere establishes possibilities that don't exist on lighter worlds. Water could stay liquid at temperatures reaching 400 degrees Fahrenheit, enabling hot springs and geysers that would instantly vaporize on Earth. The dense air would alter how sound travels. Voices would sound deeper and carry greater distances, while the increased atmospheric pressure would make weather phenomena more intense and spectacular. LHS 1140b orbits comfortably within its star's habitable zone, absorbing about 43% of the energy that Earth receives from our Sun. However, the planet's thick atmosphere could capture sufficient heat through greenhouse effects to sustain moderate surface temperatures. Computer models suggest that if this world possesses the ideal mixture of carbon dioxide and water vapor, it could nurture liquid water across most of its surface. The host star LHS 1140 provides perfect conditions for supporting life over extended time periods. This red dwarf burns consistently and peacefully, generating far fewer dangerous flares than most stars of its category. The stable energy output means that LHS 1140b has experienced relatively steady conditions for the billions of years since the system formed, providing any potential life abundant time to evolve and diversify. Recent atmospheric analysis using the James Webb Space Telescope has identified possible evidence of water vapor and other gases in LHS 1140b's atmosphere. The data suggests that this world might experience weather patterns, clouds, and perhaps even rainfall minus, all indicators that active atmospheric circulation could be distributing heat and moisture around the planet. The planet's high density creates another fascinating possibility. The massive iron core would produce a powerful magnetic field that could shield the atmosphere from being stripped away by stellar winds. This magnetic protection might explain how LHS 1140b has managed to preserve its atmosphere when so many other planets around red dwarf stars have lost theirs. If you could journey to LHS 1140b, the experience would challenge every assumption about what a livable world resembles. The 5 times stronger gravity would make every movement exhausting, but the thick atmosphere would create spectacular optical effects, deeper blue skies, more brilliant sunsets, and clouds that could tower much higher than any formations on Earth. The dense atmosphere would also establish unique opportunities for flight. The thick air would provide significantly more lift, potentially allowing large flying creatures to evolve even in the high-gravity environment. Aircraft designed for LHS 1140b could feature much smaller wings while carrying heavier loads. The planet's 25-day orbit creates rapid seasonal changes that could drive evolution in unexpected directions. Life forms might develop to exploit these quick cycles, growing rapidly during favorable seasons and entering dormancy during challenging periods. But while LHS 1140b demonstrates how a massive world might preserve its atmospheric envelope, our next destination unveils an even more Earth-like prospect, a planet so remarkably similar to our own that researchers have dubbed it Earth's cosmic twin. Stretching 300 light-years from Earth, a planet nearly identical to Earth's dimensions travels through its star's habitable zone every 19.5 days, absorbing 95% of the energy that Earth receives from our Sun. Kepler 1649c represents the closest match to Earth's size and energy absorption that we've uncovered, establishing it as potentially the most Earth-like exoplanet in our catalogue of distant realms. This extraordinary world measures precisely 1.06 times Earth's radius, making it so close to Earth's dimensions that the difference would be virtually imperceptible to a human explorer. The comparable size suggests that Kepler 1649c likely possesses similar surface gravity, atmospheric pressure, and geological mechanisms to Earth, establishing conditions where human-like life could potentially flourish without major adaptations. The planet circles a red dwarf star designated Kepler 1649, which burns significantly cooler and dimmer than our Sun. To absorb nearly identical energy as Earth, Kepler 1649c must orbit much closer to its stellar companion, completing one revolution in less than 20 Earth days. This intimate orbit means the planet is likely tidally locked, with one hemisphere bathing in eternal sunlight, while the opposite remains shrouded in perpetual shadow. The energy distribution on Kepler 1649c establishes a captivating scenario. Despite being tidally locked, the planet absorbs almost precisely the same total energy as Earth, just allocated differently across its surface. The sun-facing side might experience temperatures around 150 degrees Fahrenheit, while the shadow side could plummet to minus 100 degrees. However, if the planet maintains an atmosphere dense enough to circulate heat, the entire surface could sustain moderate temperatures. Recent computer simulations suggest that Kepler 1649c could have developed an atmospheric composition strikingly similar to Earth's. The planet's Earth-like dimensions mean it would exhibit comparable volcanic outgassing patterns and similar capacity to retain atmospheric gases. If this world began with similar initial conditions to Earth, it might have evolved to possess breathable air, liquid water oceans, and weather systems that feel familiar to terrestrial life. The discovery of Kepler 1649c emerged from a meticulous reanalysis of data from the now-retired Kepler Space Telescope. Scientists initially overlooked this planet because its transit signal resembled instrument noise so closely. Only sophisticated computer algorithms and years of careful examination revealed the regular dimming pattern that indicated a planet crossing in front of its star. This near miss in discovery illuminates how many Earth-like planets might be concealed in our existing data. Kepler 1649c suggests that Earth-sized planets in habitable zones might be vastly more abundant than we previously imagined, hidden within the noise of stellar observations, awaiting better analysis techniques to unveil them. The stellar system itself provides hints about potential habitability. Kepler 1649 contains about 75% of our Sun's mass and burns consistently without the violent outbursts that torment many red dwarf stars. The peaceful stellar environment means that Kepler 1649c has likely experienced steady conditions for billions of years, supplying ample time for complex life to develop. If Kepler 1649c harbors oceans, they would behave remarkably similarly to Earth's seas due to the comparable gravity and energy input. Tides would follow recognizable patterns. Ocean currents would emerge in response to temperature contrasts between the day and night sides, and coastal regions could experience weather patterns that echo Earth's tropical and temperate zones. The planet's swift 19.5-day orbit establishes an intriguing calendar puzzle. If intelligent life evolved on Kepler 1649 CID, the concept of a year would be incredibly brief by Earth standards. Seasonal variations, if they exist, would blur by in a matter of Earth weeks, potentially creating life forms that adapt to rapid environmental cycles. The similarity to Earth extends to potential geological activity. A planet with Earth's size and composition would likely feature plate tectonics, volcanic activity, and mountain-building processes that constantly reshape the surface. These geological mechanisms could establish diverse landscapes and provide the chemical cycling necessary to support complex ecosystems. Kepler 1649c represents the holy grail of exoplanet discovery. a world so similar to Earth that it could potentially nurture not just life, but life as we recognize it. However, our next destination reveals that even planets with ideal conditions can confront unexpected challenges that test survival's outer limits. Positioned 730 light-years away, a planet slightly larger than Neptune orbits so close to its star that it completes one revolution every 18 hours, enduring in a region where temperatures soar to 3,600 degrees Fahrenheit, scorching enough to vaporize iron. 2849b represents among the most extreme survival sagas in our galaxy, a world that appears to have been partially consumed by its star, yet lived to tell the tale. This remarkable planet exists at a distance from its star where no planet should survive. The intense radiation and stellar winds should have obliterated any atmosphere billions of years ago. Yet 2849b endures, suggesting that this world has weathered catastrophic events that would have annihilated most other planets. Scientists believe we might be observing the exposed core of what was once a much larger gas giant planet. The planet's 18-hour orbit creates the briefest year of any potentially habitable world we've discovered. Day and night cycles flash by so rapidly that the planet exists in constant flux, with temperatures fluctuating dramatically as different regions rotate into and out of the star's intense radiation. The rapid rotation might actually help distribute heat around the planet, preventing any single region from becoming too scorching to support exotic forms of life. Here's where the survival narrative becomes even more remarkable. Computer models propose that 2849b might have originated as a gas giant planet, resembling Jupiter, with a massive atmosphere of hydrogen and helium enveloping a solid rocky core. As the star evolved and intensified, the planet's orbit deteriorated, drawing it closer and closer to the stellar surface, until the outer atmosphere began vaporizing into space. The atmospheric stripping process might have consumed hundreds of millions of years, gradually exposing the dense rocky core we observe today. This core likely contains exotic materials forged under the extreme pressure of the original gas giant's atmosphere, fine diamond layers, metallic hydrogen, and other substances that could only form under conditions impossible to recreate on Earth. Tuai 849b's surface makeup challenges. Simple classification. The temperatures reach such extremes that numerous common materials exist in phases we never witness on Earth. Iron and nickel might form vast molten seas, while silicon compounds could establish flowing glass rivers. The terrain would be alien beyond comprehension, with mountains of crystallized carbon ascending from plains of liquid metal. Despite the infernal conditions, researchers speculate that 2849b might shelter life in unexpected locations, deep beneath the surface, where temperatures decline to merely several hundred degrees. Exotic biochemistry might harness the abundant energy from radioactive breakdown and chemical interactions between different molten materials. These organisms would need to rely on completely different chemistry than Earth life, possibly employing silicon or other heat-resistant materials instead of carbon. The planet's persistence offers revelations into planetary formation and development throughout the galaxy. If a world can withstand being partially devoured by its star while still maintaining its structural integrity, it implies that planetary cores are far more durable than we previously believed. Tuai 849b might represent a new category of planets, stellar survivors that emerge from close encounters with their host stars. The extreme conditions on Tuai 849b establish a natural laboratory for examining matter under circumstances we cannot replicate in Earth-based experiments. The surface pressure combined with temperatures that liquefy most materials creates states of matter that exist nowhere else in our solar system. Studying this world could teach us about the interior conditions of gas giant planets and the behavior of materials under extreme circumstances. Recent observations indicate that Tuai 849b might possess a thin atmosphere composed of vaporized rock and metal. Magnesium, silicon, and iron atoms drift in the air as individual particles, establishing an atmosphere unlike anything we've previously uncovered. This metallic atmosphere might generate spectacular visual phenomena, clouds that gleam like mirrors and lighting that radiates with the colors of different metals. The planet's closeness to its star means it experiences tidal forces powerful enough to flex the solid surface, producing additional heat through friction. This tidal heating might fuel geological activity that constantly renews the planet's surface, establishing a world where the landscape transforms dramatically over periods of just a few years. But while Tolai 849b demonstrates how planets can survive the most extreme stellar encounters, our next destination carries us to a world confronting a different kind of challenge: the delicate balance between habitability and catastrophic climate transformation. Positioned 31 light-years from Earth, a super-Earth twice our planet's size orbits at the outer boundary of its star's habitable zone, where the fragile equilibrium between ice and fire could determine whether this world becomes a paradise with flowing water or a hellscape with surface temperatures scorching enough to melt lead. GJ 357 days sits at the critical threshold where minor changes in atmospheric composition could trigger runaway greenhouse effects that transform a potentially habitable planet into something resembling Venus. This planet completes one stellar circuit every 55.7 days, positioning it at the very periphery of the zone where liquid water could exist on its surface. Computer simulations suggest that GJ 357 days absorbs roughly the same amount of energy from its star as Mars receives from our Sun, which should render it a frozen world with surface temperatures well below water's freezing point. However, the planet's larger dimensions change everything. GJ 357 days contains approximately 6.1 times Earth's mass, establishing gravity powerful enough to retain a much thicker atmosphere than smaller planets can preserve. If this atmosphere harbors even moderate amounts of greenhouse gases, like carbon dioxide or water vapor, the amplified greenhouse effect could warm the planet sufficiently to sustain liquid water across its entire surface. Here's where the narrative becomes a cautionary tale about planetary climate systems. The same atmospheric density that could render GJ 357 days habitable also makes it susceptible to runaway greenhouse warming. If excessive water vapor enters the atmosphere, it could capture so much heat that the oceans begin to boil. Water vapor is itself a potent greenhouse gas, so increased evaporation leads to enhanced warming, which leads to greater evaporation, establishing a feedback loop that could transform the planet into a steam-shrouded inferno. Researchers believe this runaway process might be occurring on GJ 357 days right now, or it might have happened billions of years ago when the planet was younger and absorbed more energy from its star. Red dwarf stars like GJ 357 gradually intensify over time, meaning this planet might have begun as a frozen world, warmed to habitability, and then continued warming until it became uninhabitable. The planet's 55-day orbit establishes seasonal fluctuations that could play a crucial role in its climate stability. As GJ 357 days moves slightly closer and farther from its star during its elliptical orbit, the changing energy input could trigger seasonal climate shifts. If the planet sits precisely at the edge of runaway greenhouse conditions, these orbital variations might push it back and forth between habitable and uninhabitable states. Recent atmospheric modeling suggests that GJ 357 days might exist in one of several possible climate conditions. In the most optimistic scenario, the planet maintains a thick but stable atmosphere that sustains surface temperatures between 32 and 100 degrees Fahrenheit, permitting liquid water oceans and Earth-like weather patterns. In the most pessimistic scenario, runaway greenhouse warming has generated surface temperatures exceeding 1,000 degrees Fahrenheit. The planet's powerful gravity would establish unique atmospheric dynamics regardless of its current climate state. Weather systems would be more intense than anything on Earth, with storms that could endure for weeks and wind patterns that redistribute heat around the planet with incredible efficiency. If GJ 357 days has preserved liquid water, its weather could include rainstorms of almost unimaginable intensity. The possibility of runaway greenhouse effects on GJ 357 days makes it a crucial test case for understanding climate stability on exoplanets. Researchers employ computer models of this world to investigate how small changes in atmospheric composition can lead to dramatic climate shifts. These studies help us comprehend not only the fate of distant worlds, but also the long-term stability of Earth's own climate. If GJ 357 days has already experienced runaway greenhouse heating, it might still shelter life in surprising locations, high within the atmospheric layers where temperatures decline to more manageable levels. Clouds of sulfuric acid could offer a refuge for floating microorganisms, similar to what some researchers propose might survive in Venus's upper atmosphere. The planet's position at habitability's threshold makes it a perfect candidate for atmospheric investigations using space telescopes. By examining the makeup of GJ 357 days atmosphere, researchers can establish whether this world represents a warning story of climate transformation or a triumph of atmospheric balance. Recent observations suggest that GJ 357 days might possess an atmosphere abundant in carbon dioxide, with hints of water vapor, indicating that the planet exists precisely at the border between habitability and runaway greenhouse conditions. This delicate equilibrium makes it among the most scientifically precious worlds for understanding how planetary climates develop over billions of years. But while GJ 357 days reveals the perils of atmospheric instability, our next destination returns us to a more recognizable scenario, a world that might be displaying Earth's own destiny. As our sun gradually intensifies and warms, 1,400 light-years away, we revisit Earth's older cousin to observe something that should both terrify and captivate us equally. A potentially habitable planet experiencing the same gradual warming that Earth will confront in roughly 1 billion years, when our sun becomes too brilliant and scorching to sustain life. Kepler 452b circles a star that's 1.5 billion years older than our sun, and this ancient system might be revealing exactly what occurs when a once-perfect world begins its slow descent toward uninhabitability. The host star Kepler 452 has been burning for approximately 6 billion years, compared to our Sun's 4.6 billion-year age. During that additional time, it has intensified by about 20% in brightness and temperature. This enhanced luminosity means that Kepler 452b now absorbs roughly 10% more energy than Earth receives from our Sun, sufficient additional heat to potentially initiate the early phases of runaway greenhouse warming that could vaporize the planet's oceans. Here's what renders this scenario both tragic and unavoidable. All Sun-like stars gradually intensify as they mature, burning their hydrogen fuel more efficiently over time. Kepler 452b might have savored billions of years of perfect Earth-like conditions with moderate temperatures, liquid water seas, and stable weather systems. But now, as its star reaches middle age, those ideal conditions are slowly vanishing. Computer models of Kepler 452b's current climate propose several possible scenarios. In the most hopeful case, the planet's atmosphere has adjusted to the increased stellar energy by developing more reflective cloud formations that redirect surplus heat back into space. White clouds and ice caps could function like mirrors, maintaining the planet cool enough to preserve liquid water despite the brighter star. However, the more probable scenario paints a grimmer picture. The surplus energy from the aging star has likely begun vaporizing more water from Kepler 452b's oceans, introducing additional water vapor into the atmosphere. Since water vapor is a potent greenhouse gas, this establishes a feedback cycle where increased evaporation leads to enhanced warming, which leads to even greater evaporation. The planet's larger dimensions might actually worsen this process. Kepler 452b contains about 60% more mass than Earth, establishing stronger gravity that enables it to retain a denser atmosphere. While this was probably advantageous when the planet was younger, the thicker atmosphere now captures more heat, accelerating the greenhouse warming mechanism. If Kepler 452b has already entered the runaway greenhouse phase, its surface might now endure temperatures scorching enough to melt sink, with atmospheric pressure dozens of times higher than Earth's. The oceans that once nurtured life would have vaporized billions of years ago, abandoning a hellish world wrapped in dense clouds of steam and carbon dioxide. But there's another possibility that offers hope for life's survival. Some researchers propose that as Kepler 452b's surface became uninhabitable, life might have migrated upward into the planet's atmosphere. High-altitude regions where temperatures remain moderate could shelter floating ecosystems of airborne microorganisms that never contact the scorching surface below. The planet's thick atmosphere might also establish opportunities for life in unexpected locations, deep underground, where surface heat cannot penetrate. Extensive cave networks could maintain moderate temperatures and host ecosystems based on geothermal energy rather than sunlight. These subterranean biospheres could persist for billions of years, completely isolated from the hostile surface conditions. Investigating Kepler 452b helps researchers understand Earth's own future. In approximately 1 billion years, our Sun will intensify sufficiently to trigger the identical runaway greenhouse effect on Earth. The oceans will vaporize, the atmosphere will become unbearably dense, and surface temperatures will climb to levels that would eliminate any known life form. However, this distant catastrophe also represents an opportunity. By the time Earth faces these conditions, human technology might be sophisticated enough to relocate our planet to a more distant orbit, or to construct massive solar shields that reduce the amount of energy reaching Earth's surface. Alternatively, we might have developed the capacity to terraform other worlds or to thrive in space habitats completely independent of planetary surfaces. The saga of Kepler 452b reminds us that habitability is not eternal. Even perfect worlds eventually become uninhabitable as their stars evolve. But life has billions of years to adapt to these gradual changes. The question is whether intelligence develops rapidly enough to discover technological solutions to cosmic-scale problems. But while Kepler 452b demonstrates the challenges of stellar aging, our next destination brings us back to the thrill of recent discovery, a world that astronomers found just months ago, adding fresh possibilities to our expanding catalogue of potentially habitable planets. Positioned 105 light-years from Earth, astronomers in late 2023 uncovered something that immediately seized the attention of planet hunters worldwide: a super-Earth 1.4 times our planet's size, orbiting directly within its star's habitable zone, where liquid water could flow across its surface. LP 899c represents among the most promising recent additions to our catalogue of potentially habitable worlds. A planet positioned so ideally for life that researchers have already started planning comprehensive atmospheric investigations. This freshly uncovered world completes its stellar circuit every 8.8 days, placing it at the optimal distance to absorb energy levels comparable to what Earth receives from our Sun. The host star LP 899 burns cooler and dimmer than our Sun, which means the planet must circle much closer to maintain warmth. But the energy equilibrium works out almost flawlessly for sustaining liquid water across the surface. The swift 8.8-day orbit establishes a year briefer than most Earth holidays. But this rapid orbital period actually assisted astronomers in finding the planet. LP 899c crosses in front of its star so regularly that researchers could observe multiple transits within merely a few weeks, confirming the planet's presence and measuring its dimensions with exceptional accuracy. The planet's size indicates it could be a rocky world hosting a considerable atmosphere, possibly dense enough to circulate heat around the planet and sustain moderate temperatures, even if it's tidally locked to its star. Computer simulations suggest that LP 899c could possess surface conditions ranging from delightfully Earth-like to spectacularly alien, depending on its atmospheric makeup and geological processes. What renders this breakthrough particularly thrilling is the timing. LP 899c was identified using data from the Transiting Exoplanet Survey satellite, TESS, which has transformed our capacity to locate planets around nearby stars. The planet exists close enough to Earth that the James Webb Space Telescope can examine its atmosphere in extraordinary detail, potentially identifying water vapor, oxygen, or other indicators of biological processes. The star LP 890 Cels 9 provides perfect conditions for nurturing life over extended time periods. This red dwarf star burns consistently without the violent outbursts that make many comparable stars hazardous to planetary atmospheres. The peaceful stellar environment means that LP 899c has likely experienced steady conditions for billions of years, supplying abundant time for life to develop and diversify. Recent follow-up observations have unveiled fascinating clues about the planet's characteristics. Measurements of how much starlight the planet blocks during transit suggest that LP 89999 might possess a thick atmosphere that extends well above its solid surface. This atmospheric envelope could indicate the presence of water vapor, carbon dioxide, or other gases that could support habitability. The planet's location in its star's habitable zone is so advantageous that some researchers have proposed it as a priority target for more intensive investigation. Ground-based telescopes are already monitoring LP 899c for signs of atmospheric fluctuations that could indicate weather systems, seasonal variations, or other dynamic processes on the planet's surface. If LP 899c harbors oceans, they would experience distinctive tidal effects due to the planet's intimate orbit around its star. Stellar tides would be far more powerful than lunar tides on Earth, potentially generating dramatic tidal ranges that expose and inundate vast coastal regions twice per 8.8-day orbital period. These extreme tides could establish unique environments where life adapts to rapid transitions between aquatic and terrestrial conditions. The discovery of LP 899c illuminates how rapidly our understanding of exoplanets is advancing. Just a few years ago, finding a potentially habitable planet dominated headlines. Now, astronomers uncover several potentially habitable worlds each year, and the challenge has transformed from finding these planets to studying them comprehensively to determine which ones actually shelter life. The planet's proximity to Earth establishes it as an ideal laboratory for testing new techniques for atmospheric analysis and characterization. Researchers plan to employ LP 899 as a prototype for investigating similar planets that might be discovered around even closer stars in the future. Recent computer simulations propose that LP 899 could maintain liquid water across a broad range of atmospheric conditions, making it more likely to be habitable than planets requiring very specific atmospheric compositions. This resilience to different environmental conditions increases the chances that this world could actually support life. The ongoing investigation of LP 899c represents the cutting edge of exoplanet science, where new discoveries emerge so rapidly that our comprehension of potentially habitable worlds continues evolving month by month. But while this newly discovered planet offers fresh possibilities, our next destination carries us to a calmer, more stable world that might represent the ideal environment for long-term biological evolution. Positioned 11 light-years from Earth, a planet slightly larger than our world orbits one of the calmest red dwarf stars ever uncovered, establishing what might be the most stable environment for life in our local cosmic neighborhood. Ross 128b absorbs energy levels similar to Earth, but its star generates virtually none of the dangerous flares and radiation tempests that torment most red dwarf systems, making this world a potential sanctuary of tranquility in a galaxy where stellar violence often obliterates planetary atmospheres. This extraordinary planet completes one stellar journey every 9.9 days, positioning it in the ideal zone where liquid water could flourish on its surface. The star Ross 128 burns with remarkable stability, displaying almost no fluctuation in brightness or magnetic activity over the decades that astronomers have observed it. This stellar serenity means that Ross 128b has probably savored billions of years of consistent, gentle energy input, perfect conditions for life to evolve and thrive. The planet's size and mass establish surface gravity approximately 1.4 times stronger than Earth's, more powerful enough to retain a substantial atmosphere, yet not so intense as to create crushing conditions. If Ross 128b possesses an Earth-like atmosphere, the surface pressure would exceed what we experience, but still remain comfortable for life forms resembling those on Earth. Ross 128b's closeness to Earth makes it among the most scientifically precious exoplanets ever discovered. At merely 11 light-years away, this world is near enough that radio signals from Earth would require only 11 years to reach it, and any response would need another 11 years to return. If intelligent life exists on Ross 128b, we could potentially establish communication within a human lifetime. The stable stellar environment surrounding Ross 128 establishes opportunities for atmospheric complexity that don't exist around more volatile stars. Without constant assault by stellar flares, Ross 128b, could have developed and preserved a layered atmosphere with distinct regions for different chemical processes. An ozone shield could safeguard surface life from harmful ultraviolet radiation, while water clouds could control temperature through reflection and greenhouse mechanisms. Computer simulations indicate that Ross 128b might exhibit weather systems strikingly similar to Earth's despite its swift 9.9-day orbit. If the planet remains tidally locked, the border between the illuminated and shadowed hemispheres could shelter a perpetual storm system that circulates heat around the planet, establishing moderate temperatures across the entire surface. The planet's probable tidal locking establishes fascinating possibilities for how life might develop there. The permanently illuminated day side could nurture photosynthetic organisms that never encounter darkness, while the shadow side might harbor chemosynthetic life forms that extract energy from chemical reactions rather than sunlight. The twilight zone between these regions could shelter the most diverse ecosystems where both types of life could flourish together. Recent observations using the European Southern Observatory's telescopes have disclosed hints that Ross 128b might possess a considerable atmosphere. Measurements of how the planet's infrared radiation fluctuates as it orbits its star suggest the presence of atmospheric gases that capture and redistribute heat. These observations represent some of the most comprehensive atmospheric investigations ever performed on such a distant world. The tranquil nature of Ross 128 means that any magnetic field produced by the planet's core would supply exceptional protection against the gentle stellar wind. Unlike planets around volatile stars that require robust magnetic fields to survive, Ross 128b could maintain a protective magnetic shield, even with a relatively modest planetary magnetic field. If Ross 128b harbors oceans, they would rank among the most stable water bodies in the galaxy, without stellar outbursts to fuel extreme weather or tidal forces to generate massive waves. These oceans could sustain consistent temperatures and chemistry for billions of years. Such stability would enable marine ecosystems to achieve incredible complexity and diversity. The planet's surface temperature likely stays remarkably steady due to the stable stellar output, without the dramatic temperature fluctuations that afflict planets around variable stars. Life on Ross 128b wouldn't need to develop extreme temperature tolerance. This could permit more delicate and specialized organisms that couldn't survive in harsher environments. Researchers have proposed Ross 128b as a perfect candidate for the next generation of extremely large telescopes currently under construction. These instruments might be powerful enough to directly capture images of the planet's surface, revealing continents, oceans, and cloud formations that could provide direct evidence of habitability or even biological processes. The discovery of Ross 128b shaped how astronomers seek potentially habitable planets. Rather than concentrating solely on planets in habitable zones, researchers now prioritize worlds around peaceful, stable stars that could provide the long-term environmental steadiness necessary for complex life to develop. But while Ross 128b represents stability and serenity, our next destination carries us to a planet much nearer to home, circling a star that we can observe with the naked eye from Earth's surface. Just 11.9 light-years from Earth, a super-Earth 4 times more massive than our world orbits a star, so comparable to our Sun that astronomers have investigated it for decades as a solar twin. TOE-CTE completes one circuit every 168 days, placing it near the inner boundary of its star's habitable zone, where liquid water could potentially exist on its surface, making this world among the closest potentially habitable planets to Earth. TOE-CETI, the star at this system's heart, has fascinated human imagination for generations because it's visible to the naked eye from Earth and burns with characteristics remarkably similar to our Sun. The star contains slightly fewer heavy elements than our Sun, which influences planetary formation in ways that could make TOE-CETI a vastly different world from Earth, despite its advantageous position in the habitable zone. The planet's considerable mass establishes surface gravity roughly twice as intense as Earth's, which would dramatically affect how any atmosphere and water systems behave. The stronger gravity enables TOE-CETI to retain a much denser atmosphere than Earth possesses, potentially creating surface pressures several times higher than what we experience. This thick atmosphere could capture sufficient heat to maintain the planet warm, despite receiving only about 60% of the energy that Earth absorbs from our Sun. Here's where the narrative becomes complicated. Computer models suggest that Tau Ceti E might be experiencing a runaway greenhouse effect, similar to what occurred on Venus. The planet's position near the inner boundary of the habitable zone, combined with its capacity to retain a dense atmosphere, could have led to surface temperatures scorching enough to vaporize water. Instead of a habitable world, Tau Ceti E might be a warning story about how rapidly planetary atmospheres can spiral beyond control. However, alternative models propose a more hopeful scenario. If Tau Ceti A possesses highly reflective clouds or surface features, it might deflect enough stellar energy back into space to sustain moderate temperatures despite its challenging orbital location. The planet could exist in a fragile balance where minor changes in cloud coverage or atmospheric composition determine whether it remains habitable or transforms into a steam-shrouded infernal world. The Tau Ceti system presents unique obstacles for planetary habitability due to its debris disks and comets that establish a far more hazardous environment than our solar system. Tau Ceti probably endures asteroid and comet impacts at rates 10 times higher than Earth, creating a constantly evolving surface where crater formation and volcanic activity reshape the landscape on relatively brief timescales. These frequent impacts could actually help sustain habitability by providing a mechanism for recycling atmospheric gases and delivering water and organic compounds to the planet's surface. Each major impact would vaporize portions of the surface, releasing trapped gases and potentially supplying the energy needed to drive complex atmospheric chemistry. The planet's 168-day orbit establishes seasons lasting approximately 42 Earth days each, much shorter than Earth seasons, yet long enough to drive significant climate variations. If Tau Ceti E possesses an atmosphere capable of storing and releasing heat, these rapid seasonal changes could generate dynamic weather patterns that distribute energy around the planet. Recent observations employing sophisticated ground-based telescopes have attempted to identify atmospheric signatures from Tau Ceti A, yet the findings remain uncertain. The planet's closeness to its brilliant star makes it extraordinarily challenging to separate the weak signal of reflected light that would unveil atmospheric makeup. Future space telescopes with enhanced capabilities for blocking stellar illumination might finally establish whether this world possesses the dense atmosphere that models forecast. The potential for life on Tau Ceti E relies heavily on how effectively organisms could adjust to the high-impact environment and potentially severe atmospheric conditions. Life forms might need to develop advanced repair systems to handle radiation from frequent impacts, or they might withdraw to subterranean environments where they're shielded from surface disasters. If Tau Ceti A has preserved liquid water despite its demanding conditions, those seas would be unlike anything on Earth. The elevated atmospheric pressure could enable water to stay liquid at temperatures far above Earth's boiling point, establishing hot, dense oceans that could nurture exotic biochemistry based on heat-loving organisms. The planet's nearness to Earth establishes it as a priority candidate for future interstellar missions. At less than 12 light-years distant, Tau Ceti E could potentially be accessed by advanced spacecraft within a century or two, making it among the most probable destinations for humanity's first voyage to another potentially habitable world. Recent breakthroughs in telescope technology have enabled astronomers to investigate the Tau Ceti system with unprecedented precision, revealing that it might harbor additional planets that could provide alternative habitable environments if Tau Ceti E proves too extreme for life. But while Tau Ceti A confronts us with questions about habitability in high-energy environments, our next destination carries us to a completely different type of world, a planet where water might be so plentiful that land becomes a rare and valuable resource. Positioned 1,200 light-years away, a planet 1.4 times Earth's dimensions orbits at the distant boundary of its star's habitable zone, and computer simulations suggest something remarkable. This world might be entirely blanketed by a global ocean with no continents or islands piercing the surface. Kepler-62e represents our strongest candidate for a genuine water world, a planet where life would develop entirely in aquatic environments and where the concepts of land and sky might be completely foreign. This super-Earth completes one stellar journey every 267 days, positioning it at roughly the same distance from its sun as Venus maintains from ours. However, Kepler-62e's host star burns significantly cooler and dimmer than our sun, supplying precisely the right amount of energy to prevent Kepler-62e's global ocean from crystallizing while stopping it from vaporizing into space. The planet's larger dimensions establish several conditions that encourage the formation of a water world. The enhanced gravity helps Kepler-62e retain a thick atmosphere that could capture sufficient heat to maintain water liquid even at its remote orbit. Additionally, the planet's formation process likely delivered vastly more water than Earth received, establishing oceans that could be hundreds of miles deep, deep enough to submerge any mountains or continents that might attempt to rise above the surface. Here's what renders Kepler-62e particularly captivating. Without continents to establish shallow seas and tidal zones, life would need to develop in a completely three-dimensional environment. There would be no shorelines, no coral reefs in shallow water, and no transition zones between aquatic and terrestrial life. Instead, ecosystems would emerge in layers throughout the water column, from the sunlit surface zones down to the crushing depths near the ocean floor. The global ocean would establish weather patterns unlike anything on Earth. Without land masses to interrupt airflow, Kepler-62e could develop planet-spanning storm systems that encircle the globe in massive spirals. These super-hurricanes might endure for months or years, driven by temperature contrasts between the warm equatorial waters and the cooler polar regions. Marine life on Kepler-62e would confront unique evolutionary pressures. Without shallow water environments, organisms might need to develop sophisticated buoyancy control to navigate the vast three-dimensional ocean. Swimming creatures could potentially grow much larger than anything in Earth's oceans, exploiting the deep water and absence of size constraints imposed by shallow areas. The lack of land would establish challenges for developing technology and civilization. Any intelligent life that evolved on Kepler-62e would need to construct tools and structures from materials available in the ocean, perhaps cultivating coral-like cities or developing biotechnology based on modified marine organisms. The concept of fire, metallurgy, and many other land-based technologies would be completely alien to ocean-dwelling intelligence. Computer models indicate that Kepler-62e's thick atmosphere might generate a substantial greenhouse effect that maintains the entire planet at moderate temperatures, potentially allowing liquid water to exist even at the polar regions. The global ocean would function as a massive thermal reservoir, storing heat during the planet's day and releasing it during the night to sustain stable temperatures. The planet's 267-day orbit establishes extended seasons that would drive major shifts in ocean circulation patterns. As different hemispheres receive varying amounts of stellar energy during the planet's year, massive currents would emerge to redistribute heat around the globe, creating seasonal migrations of nutrients and marine life that could span thousands of miles. Deep beneath Kepler-62e's global ocean, the seafloor might host extensive hydrothermal vent systems where volcanic activity supplies energy for chemosynthetic ecosystems. These deep-sea communities could develop independently of surface life, establishing parallel evolutionary pathways that lead to completely different types of organisms. The thick atmosphere and global ocean would generate unique optical effects that would make Kepler-62e's sky unlike anything we observe on Earth. Light filtering through the dense air and reflecting off the ocean surface could create perpetual rainbows, while the absence of land features would mean that the horizon appears perfectly smooth in all directions. Recent atmospheric modeling suggests that Kepler-62e might have clouds that form at multiple elevations, establishing layered weather systems that could produce complex precipitation patterns. Rain, snow, and possibly even more exotic forms of precipitation could fall through the thick atmosphere into the global ocean, driving chemical cycles that sustain marine ecosystems. If life exists on Kepler-62e, it would represent a completely independent experiment in biological evolution, developing in an environment so different from Earth that the resulting organisms might challenge our fundamental assumptions about how life can adapt and flourish. The investigation of Kepler-62e helps researchers understand how common water worlds might be throughout the galaxy, and whether such planets could support complex life despite their lack of traditional land-based environments. But while Kepler-62e demonstrates the possibilities of life in a global ocean, our next destination carries us beyond individual planets to investigate how revolutionary techniques for studying distant atmospheres are transforming our comprehension of habitability across the galaxy. Positioned 1,150 light-years from Earth, a planet slightly smaller than Jupiter has emerged as one of the most extensively examined worlds in our galaxy. Not because it could shelter life, but because it's instructing us how to identify the atmospheric signatures that could unveil habitability on distant Earth-like planets. WASP-96b circles so intimately close to its star that its atmosphere soars to 2,000 degrees Fahrenheit, establishing a natural laboratory where astronomers can master the techniques that will eventually uncover signs of life on more welcoming worlds. This scorching gas giant completes one stellar circuit every 3.4 days, qualifying it as what astronomers classify as a hot Jupiter, a massive planet that migrated inward from the outer reaches of its solar system to orbit perilously close to its star. The extreme heat has inflated WASP-96b's atmosphere, rendering it larger and less dense than Jupiter, despite possessing similar mass. The planet's expanded atmosphere establishes perfect conditions for atmospheric spectroscopy, the technique that enables researchers to identify gases in distant planetary atmospheres by examining how they absorb starlight. When WASP-96b transits across its star's face, different atmospheric gases absorb specific wavelengths of light, generating a chemical fingerprint that unveils the atmosphere's composition in extraordinary detail. Recent observations employing the James Webb Space Telescope have identified water vapor, clouds, and atmospheric haze in WASP-96b's atmosphere with unprecedented accuracy. While this blistering world could never nurture life, the identical techniques used to investigate its atmosphere can be applied to potentially habitable planets to seek water vapor, oxygen, ozone, and other gases that could indicate biological processes. The breakthrough emerged from analyzing how starlight shifts color as it filters through WASP-96b's atmosphere during transit. Different molecules absorb distinct wavelengths of light, so by measuring which colors get absorbed, researchers can determine precisely which gases exist in the planet's air. This technique performs so effectively that astronomers can detect atmospheric components comprising less than 1 part per million of the total atmosphere. WASP-96b's atmosphere harbors water vapor, despite surface temperatures scorching enough to liquefy copper. This discovery proves that water can persist in planetary atmospheres under far more extreme conditions than researchers previously believed, broadening the range of planets where we might expect to discover water signatures in the future. The planet's cloud formations have unveiled unexpected complexity in hot Jupiter atmospheres. High-altitude clouds composed of condensed metals and exotic compounds establish weather patterns spanning thousands of miles, driven by temperature contrast between the illuminated and shadowed sides of the tidally locked planet. These massive storm systems redistribute heat and chemicals around the planet in ways that generate detectable variations in the atmospheric spectrum. Researchers employ WASP-96b as a standard for testing new atmospheric analysis techniques before applying them to potentially habitable planets. The planet's brilliant star and distinct atmospheric signatures make it easier to investigate than smaller, cooler worlds, enabling scientists to refine their methods and understand their instruments' limitations. The atmospheric analysis has disclosed that WASP-96b contains significantly less sodium than comparable planets, suggesting that this world formed in a different region of its solar system or experienced distinct evolutionary processes. These compositional differences teach researchers how planetary formation influences atmospheric chemistry, providing insights that help interpret observations of potentially habitable worlds. Temperature mapping of WASP-96b's atmosphere has demonstrated that the day side reaches over 2,000 degrees Fahrenheit, while the night side remains slightly cooler, generating powerful winds that transport heat around the planet. Understanding these thermal transport mechanisms helps researchers model atmospheric circulation on planets in habitable zones where similar processes could determine whether a world maintains moderate temperatures suitable for life. The planet's investigation has pioneered techniques for detecting atmospheric escape, where superheated gases stream away from the planet into space. WASP-96b loses thousands of tons of atmosphere every second, yet its massive size means it can sustain this loss for billions of years. Similar measurements on smaller planets could reveal whether they've preserved sufficient atmosphere to support habitability. Recent observations have identified subtle chemical reactions occurring in WASP-96b's upper atmosphere, where ultraviolet radiation from the star fragments molecules and creates new compounds. These atmospheric chemistry studies provide blueprints for understanding how stellar radiation affects planetary atmospheres, crucial information for evaluating habitability around different stellar types. The precision achieved in investigating WASP-96b's atmosphere represents a revolution in exoplanet science. For the first time, researchers can analyze the detailed chemical composition of a world circling another star, bringing us tantalizingly close to the day when we might detect definitive biosignature gases in the atmosphere of a potentially habitable planet. The techniques developed through studying WASP-96b are now being applied to smaller, cooler planets that might actually harbor life. Each atmospheric analysis brings us one step closer to answering the fundamental question of whether Earth is unique or whether life flourishes throughout the galaxy. But while WASP-96b demonstrates how to detect atmospheric signatures, our next destination carries us to a world that has already produced mysterious signals that briefly made researchers wonder if we had detected our first indication of alien intelligence. Position 94 light-years from Earth, a planet slightly larger than Neptune orbits a sun-like star, and in 2016, this distant world became the epicenter of one of the most fascinating potential city detections in recent history, when radio telescopes captured a powerful signal that appeared to originate from the HD 164595 system. While the signal was later explained as terrestrial interference, the incident illuminated how close we might be to detecting genuine communications from distant civilizations. The BO 64595b completes one orbital journey around its star every 40 days, positioning it too close to its sun to be habitable by Earth standards. Surface temperatures likely surpass 1000 degrees Fahrenheit, rendering this world hostile to life as we understand it. However, the planet's discovery sparked fascinating questions about whether other, more hospitable worlds might exist in the identical system, potentially sheltering the intelligent life that could have generated the enigmatic radio transmission. The signal identified from HD 164595 registered at a frequency of 11 GHz with an intensity that would have demanded tremendous amounts of energy to produce if it genuinely originated from the stellar system. The power levels were so elevated that any civilization capable of creating such a signal would require technology far beyond anything humans have achieved, potentially representing a Type II civilization on the Kardashev scale, one capable of capturing the entire energy output of its star. Radio astronomers initially found it challenging to explain the signal's characteristics. It persisted for several minutes, displayed no obvious pattern or modulation that would suggest natural origin, and emanated from a precise direction in space that matched the HD 164595 system. The signal's frequency and duration aligned with theoretical predictions for how an advanced alien civilization might attempt to communicate with distant worlds. Follow-up observations employing multiple radio telescopes worldwide failed to identify any recurring signals from HD 164595, which immediately raised skepticism about the extraterrestrial origin hypothesis. Authentic signals from alien civilizations would likely repeat or demonstrate some pattern of transmission, rather than appearing once and never returning. The absence of follow-up signals indicated that the original detection might have been caused by human technology rather than alien intelligence. The investigation into the HD 164595 signal revealed how challenging it can be to distinguish between genuine extraterrestrial communications and terrestrial interference. Satellites, military radar systems, and even microwave ovens can generate radio signals that appear to originate from space when they bounce off aircraft or satellites in Earth's orbit. The HD 164595 signal was eventually traced to a military satellite that briefly transmitted on the same frequency as the apparent alien signal. However, The incident provided invaluable lessons for the search for extraterrestrial intelligence SETI community. It demonstrated how rapidly potentially significant signals can be detected and analyzed, and it showed that the international astronomy community is prepared to investigate unusual signals with appropriate scientific rigor. The protocols developed for investigating the HD 164595 signal now serve as blueprints for evaluating future potential SETI detections. The HD 164595 system itself remains scientifically compelling even without alien signals. The star is remarkably similar to our Sun in mass, temperature, and age, making it the type of star most likely to support habitable planets. While HD 164595b is too scorching for life, computer models suggest that additional planets could exist in the system's habitable zone, potentially providing environments where liquid water and life could flourish. Advanced telescopic searches have not yet identified any additional planets in the HD 164595 system, but current instruments can only locate relatively large planets that pass directly in front of their star as viewed from Earth. Earth-sized planets in the habitable zone could easily exist in this system without being detectable by current technology, leaving open the possibility that HD 164595 hosts worlds where life might actually evolve. The false alarm HD 164595 highlights both the promise and the obstacles of searching for extraterrestrial intelligence. Radio telescopes are now sensitive enough to detect artificial signals from civilizations thousands of light years away, but they're also sensitive enough to detect countless sources of interference from human technology. Distinguishing between genuine alien signals and false alarms requires careful analysis and multiple independent confirmations. Recent improvements in radio telescope technology and signal processing have reduced the likelihood of false SETI detections while increasing sensitivity to genuine extraterrestrial signals. Automated systems now monitor millions of stars simultaneously, searching for the types of artificial signals that could only be produced by intelligent civilizations. The HD 164595 incident reminds us that the discovery of extraterrestrial intelligence might come not from a carefully planned observation of a nearby potentially habitable planet, but from an unexpected signal detected during routine monitoring of star systems that seemed unremarkable. Any stellar system could potentially harbor intelligent life, even if the planets we've detected there seem unsuitable for biology. The continued investigation of HD 164595 and similar systems keeps alive the possibility that somewhere among the thousands of known exoplanets, a civilization might be attempting to communicate with us right now, transmitting signals across the vast distances of interstellar space in hopes of making contact with other intelligent species. But while HD 164595b teased us with the possibility of alien intelligence, our next destination carries us to a world that sits precariously on the boundary between habitability and hostile conditions, where the difference between life and death might depend on the density of the atmosphere. Positioned 16 light-years from Earth, a super-Earth 5 times more massive than our world orbits, at the very periphery of its star's habitable zone, where computer simulations suggest it could be either a temperate planet with flowing water or a runaway greenhouse world with surface temperatures scorching enough to melt lead. Gliese 832c represents one of the most uncertain cases in our catalogue of potentially habitable planets. A world where minor differences in atmospheric composition could determine whether it nurtures life or remains forever barren. This massive planet completes one stellar circuit every 36 days, positioning it at the inner threshold of the zone where liquid water could theoretically exist on its surface. The planet absorbs roughly the same amount of energy from its star as Earth receives from our Sun, but its larger mass enables it to retain a much denser atmosphere that could either provide beneficial greenhouse warming or trigger catastrophic overheating. The uncertainty surrounding Gliese 832c stems from our limited understanding of how super-Earth atmospheres behave. Computer models generate dramatically different outcomes depending on the assumptions about atmospheric composition, with some scenarios displaying moderate Earth-like temperatures and others predicting Venus-like conditions with surface temperatures exceeding 800 degrees Fahrenheit. In the optimistic scenario, Gliese 832c has developed an atmosphere containing precisely the right amount of greenhouse gases to maintain moderate temperatures despite its position at the edge of the habitable zone. Water vapor, carbon dioxide, and other atmospheric gases could establish a thermal blanket that maintains the planet warm enough for liquid water while reflecting sufficient heat back into space to prevent runaway warming. However, the pessimistic scenario depicts a far grimmer picture. The planet's powerful gravity could have enabled it to preserve hydrogen and helium from its formation, establishing a dense primordial atmosphere that captures enormous amounts of thermal energy. Alternatively, volcanic outgassing across billions of years could have injected so much carbon dioxide into the air that Gliese 832c now endures a runaway greenhouse effect, resembling Venus. The planet's 36-day orbital cycle establishes seasonal fluctuations that could play a decisive role in determining its climate stability. As Gliese 832c moves nearer and farther from its star during its slightly oval-shaped orbit, the varying energy input could either stabilize temperatures through feedback mechanisms or push the planet between different climate conditions. Recent attempts to identify atmospheric signatures from Gliese 832c have yielded inconclusive findings. The planet's red dwarf host star is significantly dimmer than Sun-like stars, making it challenging to collect sufficient light to examine the planet's atmospheric makeup using current telescope technology. Future instruments with enhanced sensitivity might finally establish whether this world has preserved a habitable atmosphere or succumbed to greenhouse heating. The star Gliese 832 presents both benefits and obstacles for planetary habitability. Red dwarf stars burn for trillions of years, supplying stable energy for vastly longer periods than Sun-like stars. However, many red dwarfs generate violent outbursts during their youth that can obliterate planetary atmospheres. Gliese 832 appears relatively peaceful, but any historical flare activity could have dramatically transformed the planet's atmospheric development. If Gliese 832c has preserved habitable conditions, it would experience a vastly different environment from Earth due to its intense gravity and rapid orbit. Surface gravity 5 times more powerful than Earth's would make movement demanding for any life forms, but it would also enable much denser atmospheres and more spectacular weather patterns than we observe on our planet. The planet's probable tidal locking adds additional complexity to climate modeling. With one hemisphere perpetually facing the star and the opposite in eternal shadow, temperature contrasts between the illuminated and dark sides could fuel powerful atmospheric circulation patterns that either stabilize global temperatures or generate extreme weather conditions incompatible with life. Atmospheric escape represents another critical factor in Gliese 832c's habitability. Even though the planet's powerful gravity helps it preserve atmospheric gases, the intimate orbit exposes it to intense stellar radiation that could gradually erode lighter atmospheric components across billions of years. The equilibrium between atmospheric retention and loss could determine whether this world remains habitable over geological timescales. Researchers employ Gliese 832c as a test case for developing superior climate models for super-Earth planets. The uncertainties surrounding this world highlight the gaps in our comprehension of how planetary atmospheres develop around red dwarf stars, driving research that will help us better evaluate the habitability of similar planets discovered in the future. The ongoing debate about Gliese 832c's habitability demonstrates how much we still need to discover about exoplanet atmospheres. Even with our most advanced computer models and observational techniques, we cannot definitively establish whether this nearby world represents a potential home for life or a warning story about the fragility of planetary climates. Future missions to investigate Gliese 832c could provide crucial insights into super-Earth habitability that would inform our understanding of potentially habitable planets throughout the galaxy. The lessons learned from this uncertain world could help us identify which of the thousands of known exoplanets are most likely to actually nurture life. But while Gliese 832c confronts us with questions about atmospheric stability, our next destination carries us to an even more perilous world, a planet that might possess all the ideal conditions for life, except for the lethal radiation that regularly bathes its surface. Positioned 470 light-years away, a planet just 12% larger than Earth, circles directly in its star's habitable zone, absorbing almost precisely the same amount of energy that Earth receives from our Sun. Kepler 438b should rank among the most promising candidates for habitability in our galaxy. Yet this world confronts a deadly challenge that could render its surface uninhabitable for any known form of life. SIT orbits a red dwarf star that regularly unleashes radiation flares 10 times more powerful than the most violent solar storms our Sun has ever produced. This near-Earth-sized world completes one stellar journey every 35 days, positioning it at the optimal distance where liquid water could flourish on its surface under normal circumstances. The planet's dimensions suggest it likely possesses similar gravity to Earth, and computer simulations indicate it could sustain an Earth-like atmosphere if not for the constant assault of high-energy radiation from its hyperactive star. Kepler 438, the red dwarf star at this system's center, represents one of the most magnetically violent stars known to astronomy. Every few hundred days, the star generates super flares that amplify its brightness by up to 10% and assault nearby planets with X-rays and ultraviolet radiation intense enough to obliterate atmospheric gases, molecule by molecule. These radiation tempests make the most powerful solar flares from our Sun appear like gentle breezes by comparison. The regular super flares establish a hostile environment that would challenge even the most radiation-resistant life forms known on Earth. During a typical flare event, Kepler 438b receives roughly 100 times more high-energy radiation than Earth experiences during the most intense geomagnetic storms. This level of radiation would fragment water molecules in the atmosphere, annihilate ozone layers, and create surface conditions lethal to most biological processes. However, the saga of Kepler 438b might not be entirely hopeless. Computer simulations suggest that if the planet possesses a remarkably strong magnetic field, much more powerful than Earth's, it might deflect enough stellar radiation to establish small safe zones on its surface. These protected regions could potentially shelter life in underground caverns or deep ocean environments where the worst radiation effects cannot penetrate. The planet's atmospheric envelope, if it continues to exist, would remain in perpetual turmoil due to the relentless radiation assault. During peaceful intervals between outbursts, atmospheric gases could gather and establish more temperate surface conditions, but each super flare would tear away portions of the atmosphere, establishing a rhythm where the planet's livability strengthens and weakens over periods of hundreds of Earth days. Recent atmospheric modeling indicates that Kepler 438b might have developed distinctive atmospheric chemistry in response to the radiation environment. Gases that would typically be obliterated by ultraviolet light might survive due to rapid chemical recycling processes fueled by the high-energy radiation. The outcome could be an atmosphere completely unlike anything in our solar system, with exotic chemistry that could either nurture unusual forms of life or render the surface entirely hostile. The planet's 35-day orbital cycle adds another dimension of complexity to its radiation environment. As Kepler 438b travels nearer and farther from its star during its slightly oval-shaped orbit, the intensity of radiation bombardment fluctuates dramatically. The planet might experience intervals of relative tranquility, alternating with periods of severe radiation exposure, establishing environmental cycles that could fuel unique evolutionary adaptations. If life flourishes on Kepler 438b, it would need to be exceptionally hardy against radiation damage. Organisms might develop advanced DNA repair systems that can mend genetic damage caused by high-energy particles, or they might evolve cellular structures that protect vital components from radiation exposure. Some life forms might even adapt to harness the abundant high-energy radiation as an energy source rather than depending on chemical processes or photosynthesis. The subterranean environment on Kepler 438b could offer sanctuary from surface radiation while still permitting complex ecosystems. Caverns, underground streams, and subsurface seas could shelter communities of organisms that venture to the surface only during peaceful periods between stellar outbursts. These underground biospheres could endure for billions of years, completely separated from the hostile surface conditions. The investigation of Kepler 438b has shaped how researchers think about habitability around red dwarf stars. While these compact stars supply stable energy for trillions of years, their tendency to generate violent outbursts might make them less suitable for nurturing life than previously believed. This research has sparked renewed interest in planets around Sun-like stars, which provide more consistent and less hazardous radiation environments. Recent breakthroughs in telescope technology might soon enable direct detection of atmospheric escape from Kepler-438b, supplying definitive proof of how stellar flares impact planetary atmospheres. These observations could establish whether this potentially habitable world has succeeded in preserving sufficient atmosphere to sustain life despite the constant radiation bombardment. The ongoing investigation of Kepler-438b represents a vital test of life's capacity to endure in high radiation environments. If biological processes can survive on this battered world, it would dramatically broaden our comprehension of where life might exist throughout the galaxy, including around the most abundant type of stars in the Milky Way. But while Kepler-438b demonstrates the challenges of surviving stellar violence, our expedition now reaches its pinnacle. As we explore what the future might hold for our quest for life among the stars, somewhere in our galaxy, circling a star we haven't yet identified, a planet awaits that will revolutionize humanity's understanding of our place in the universe. This world might be nearer than Proxima Centauri b, or more distant than Kepler-452b, more massive than a super-Earth or smaller than Mars. But when we locate it, this planet will deliver the first undeniable evidence that life exists beyond Earth, ending the cosmic isolation that has characterized human existence throughout our entire history. The breakthrough might emerge from the James Webb Space Telescope, identifying oxygen and water vapor in the atmosphere of a planet orbiting a nearby red dwarf star. Oxygen is so chemically reactive that it vanishes from planetary atmospheres within a few million years, unless something continuously replenishes it, and on Earth, that something is life. Discovering oxygen in another world's atmosphere, especially combined with water vapor and other biological gases, would represent the definitive evidence that biology has established itself on another world. Alternatively, the revelation might come from radio telescopes identifying artificial signals from a civilization thousands of light years away. These transmissions could range from intentional attempts at interstellar communication to the accidental spillover of powerful broadcasts from an advanced technological society. The first confirmed detection of extraterrestrial intelligence would reveal that not only does life exist elsewhere, but that evolution can generate consciousness and technology on multiple worlds. The discovery could even emerge from much closer to home, within our own solar system. Upcoming missions to Jupiter's moon Europa and Saturn's moon Enceladus will seek life in the subsurface oceans that exist beneath these worlds' icy shells. Finding even microscopic life in these alien seas would prove that biology can emerge independently in multiple locations within a single stellar system, suggesting that life might be remarkably abundant throughout the galaxy. Advanced artificial intelligence might accelerate the pace of discovery by examining vast datasets from space telescopes in ways that human researchers never could. Machine learning algorithms could recognize subtle patterns in exoplanet observations that reveal atmospheric biosignatures currently concealed in the noise of stellar fluctuation. AI systems might uncover hundreds of potentially habitable worlds in existing data that we've missed using conventional analysis methods. The next generation of extremely large telescopes currently under construction will transform our capability to investigate exoplanet atmospheres. These instruments will be powerful enough to directly capture images of Earth-sized planets orbiting nearby stars, revealing not just atmospheric composition, but also surface features like continents, oceans, and cloud formations. We might observe weather systems on alien worlds, witness seasonal transformations unfolding on distant planets, and monitor the day-night boundaries on tidally locked worlds. The future space missions could elevate atmospheric analysis to unprecedented levels of accuracy. Proposed space telescopes designed specifically for exoplanet observation could identify biosignature gases at concentrations millions of times lower than current instruments can detect. These missions could not only confirm the presence of life, but also determine what types of organisms exist on distant worlds by examining the specific chemical signatures they leave in planetary atmospheres. The discovery of life beyond Earth will likely emerge not from a single dramatic observation, but from the gradual accumulation of evidence across multiple worlds and multiple types of investigations. We might initially identify potential biosignatures in one planet's atmosphere, then discover comparable signatures across several other worlds, constructing a case for extraterrestrial life through statistical evaluation rather than conclusive proof from any individual planet. Breakthroughs in theoretical biology might help us identify forms of life that don't resemble terrestrial biology. Researchers are creating models for how life might develop using different chemical foundations than Earth biology, potentially based on silicon rather than carbon or employing liquid methane instead of water. Recognizing these alternative life forms could broaden our search to encompass worlds that currently appear too harsh for biology. The consequences of uncovering extraterrestrial life will reach far beyond science into philosophy, religion, and human culture. Finding even microscopic life on another world would demonstrate that Earth is not exceptional, while discovering intelligent extraterrestrial civilizations would fundamentally transform how humans perceive themselves in the cosmic hierarchy. These discoveries could unite humanity around our shared identity as one species among many in a galaxy brimming with life. International collaboration in space exploration will become even more vital as we approach detecting extraterrestrial life. The discovery will likely demand verification from multiple independent sources and meticulous analysis by researchers from around the world. The protocols we establish for announcing and investigating the first confirmed extraterrestrial life will create precedents for how humanity manages one of the most momentous discoveries in our history. The quest for life beyond Earth represents more than mere scientific curiosity. It addresses fundamental questions about whether intelligence and consciousness are rare cosmic accidents or inevitable outcomes of planetary evolution. The answers we uncover among the stars will determine whether humanity confronts the future alone or as part of a vast community of conscious beings distributed throughout the galaxy. But as we stand on the brink of these magnificent discoveries, we must also contemplate what all these distant worlds mean for humanity's own cosmic voyage. The catalogue of potentially habitable exoplanets we've explored represents more than a collection of distant curiosities. These worlds map a pathway for humanity's expansion beyond Earth and offer glimpses of what our species might become as we disperse among the stars. From the tidally locked Proxima Centauri b, just 4 light-years away, to the ancient Kepler 452b, revealing Earth's distant future, each of these planets teaches us something essential about the challenges and opportunities that await us in the cosmos. Our nearest, potentially habitable neighbor, Proxima Centauri b, could become humanity's first destination beyond our solar system. At 4.2 light-years distant, this world represents our closest approach to interstellar travel, with technologies we might develop within the next century. Advanced spacecraft employing fusion propulsion, or even more exotic technologies like antimatter engines, could potentially reach Proxima Centauri b within 50 to 100 years, making it possible for humans alive today to witness our species take its first steps toward becoming an interstellar civilization. The diverse array of habitable worlds we've uncovered expands our options for future colonization far beyond Earth-like planets. Super-Earths like LHS 1140b and 2I 715b demonstrate that habitable worlds might typically be larger and more massive than Earth, with enhanced gravity and denser atmospheres. Humans colonizing such worlds would need to adjust to these conditions, perhaps developing new technologies for movement and construction in high-gravity environments, or even evolving different physical characteristics across many generations. Tidally locked planets like TRAPPIST-1e and Gliese 667 cc challenge us to think innovatively about how human civilization might flourish on worlds where one hemisphere experiences eternal daylight while the other remains in perpetual darkness. These planets could host cities in the twilight zones where temperatures stay moderate, with transportation networks linking the resource-rich sides to energy-generating facilities that could exploit the temperature differences between hemispheres. The water worlds like Kepler 62e hint at completely different types of human societies that might emerge on planets with no land masses. Floating cities, underwater habitats, and marine-based agriculture could sustain human populations on worlds blanketed entirely by deep oceans. These aquatic civilizations might develop technologies and cultures drastically different from anything possible on land-based worlds. The violent stellar environments around planets like Wolf 1061c and Kepler 438b could fuel the development of advanced radiation shielding technologies and subterranean civilizations. Humans settling such worlds might become masters of defensive technology, constructing cities deep beneath planetary surfaces and developing biotechnology that enhances radiation resistance. These skills could prove invaluable for surviving in other hostile environments throughout the galaxy. The long-term survival of human civilization might depend on spreading across multiple stellar systems to avoid catastrophic events that could affect entire solar systems. Supernova explosions, gamma-ray bursts, and other cosmic disasters could sterilize planets across hundreds of light years. But a civilization distributed among many stellar systems would be virtually impossible to eliminate completely. The exoplanets we've discovered provide thousands of potential refuges for humanity's future. Each potentially habitable world offers unique opportunities for scientific research and technological advancement. The extreme conditions on planets like TOI 849b could advance materials science and high-energy physics, while the atmospheric complexity of worlds like K218b could drive innovations in climate engineering and atmospheric management. Human settlements across diverse exoplanets could become specialized research centers that expand the boundaries of knowledge in different fields. The discovery of extraterrestrial life on any of these worlds would fundamentally alter humanity's cosmic perspective and priorities. Finding even microbial life would prove that biology can emerge independently on multiple worlds, suggesting that life is abundant throughout the galaxy. Discovering intelligent alien civilizations would create opportunities for cultural and technological exchange that could accelerate human development by thousands of years. The challenges of reaching and settling exoplanets will drive technological innovations that benefit life on Earth as well. Developing closed-loop life support systems for interstellar voyages could help solve environmental problems on Earth, while learning to terraform hostile exoplanets could provide tools for reversing climate change or adapting to environmental shifts on our home world. As we contemplate humanity's expansion to the stars, we must also consider our responsibilities as a spacefaring species. The potentially habitable worlds we've discovered might already shelter life, requiring us to develop ethical frameworks for interacting with alien ecosystems and protecting extraterrestrial environments. Human colonies on exoplanets must strike a delicate balance between the requirements of human civilization and reverence for any existing biological communities. The expedition to these remote worlds will likely extend across many human generations, demanding that we establish sustainable space-based civilizations capable of maintaining themselves during century-long voyages between stellar systems. These traveling communities could evolve into their own distinctive cultures, potentially as different from Earth-based humanity as any alien civilization we might discover. The potentially habitable exoplanets distributed throughout our local galactic region represent stepping stones toward an even more magnificent future, a time when human civilization encompasses hundreds or thousands of stellar systems, when our species has become truly cosmic in scope. Each world we've investigated brings us closer to comprehending what that future might resemble and how we might achieve it. The stars are beckoning, and these distant worlds illuminate the path forward. Humanity's cosmic destiny begins with the next generation of space telescopes, interstellar probes, and perhaps even the first human expeditions beyond our solar system. The potentially habitable planets we've uncovered today could become the homes where our descendants will dwell, labor, and dream beneath alien suns, carrying the flame of human consciousness to worlds we can barely envision. From the twilight regions of tidally locked worlds to the overwhelming gravity of super-Earths, from the subterranean seas of frozen planets to the metallic vapor atmospheres of stellar survivors, our expedition through the galaxy's most promising habitable worlds unveils a cosmos far more bizarre and magnificent than we ever conceived. These remarkable destinations represent merely the opening chapter of humanity's quest for life beyond Earth, and perhaps our first preview of the worlds where our species will someday establish residence. The potentially habitable exoplanets distributed throughout our cosmic vicinity offer both promise and obstacles. They demonstrate that Earth-like conditions might be abundant throughout the galaxy, but they also expose the remarkable diversity of environments where life might flourish. From planets assaulted by stellar radiation to worlds trapped in perpetual twilight, each destination instructs us something fresh about the possibilities and boundaries of habitability in our universe. As we stand at the dawn of an era when space telescopes will examine alien atmospheres for traces of life, when interstellar probes might explore nearby stellar systems, and when humanity embarks on its first steps toward becoming a truly spacefaring civilization, these distant worlds illuminate the pathway forward into our cosmic destiny. The next time you gaze upward at the night sky, remember that among those infinite points of light, worlds await where alien sunsets splash strange landscapes in hues we've never witnessed, where tempests rage for decades across global seas, and where life might already be composing its own extraordinary tale in the language of chemistry and evolution. Don't forget to subscribe for more cosmic adventures, and share in the comments which of these incredible worlds you'd most want to explore. The universe is immense, enigmatic, and more astounding than we could ever dream.